Good morning, and thank you very much for having me. This paper is joint work with Dennis, who is also here somewhere. So one of the reasons why we started working on this project is the fact that we've seen a lot of recent work on non-parametric versions of instrumental variable estimation in the econometrics and especially econometric theory sort of literature. But it seems like these estimators have not really yet enjoyed the same or similar popularity as the linear IV methods that are really used in applied work everywhere. And we think that there's at least one main reason why that might be the case is that non-parametric IV estimators are known to possibly suffer from very, very poor performance in the sense of having slow convergence rates. And we were thinking, we're trying to see whether we can do something about this and perhaps make these non-parametric IV methods a bit more attractive to applied people. We know already that from the theory literature that these slow convergence rates are optimal. And so the only way you can really get estimators that perform perhaps better in some sense by putting more restrictions on the model. We will propose to impose two conditions at the same time, two restrictions. These come in the form of shape restrictions, and we want to argue that these shape restrictions can potentially have a very, very large impact on the estimator's performance. We have two conditions, two restrictions. The first one is a monotonicity restriction on the regression function itself. This is the regression function, the object of interest, the one that you want to estimate. We assume that it's either increasing or decreasing. And then we have a monotonicity assumption also on the instrument that's available. Essentially, and I'll be much more precise about this, but essentially what it means is that the instrument has to have a monotone relationship with the endogenous variable in the model. With these two restrictions, we can show a couple of things. The first one is stated a bit vaguely at the moment, but I'll be much more precise about this later, is that ill-posedness of the model, and I'll talk a bit about this, which is, ill-posedness is the part that, the feature of the model that is really causing these slow convergence rates. We want to argue that ill-posedness is weakened in some sense under these two conditions, and therefore there is an impact of these two restrictions on the performance of the estimator. First of all, we can say that imposing these two restrictions will not in general lead to worse performance than if you don't impose them in an estimator. So in particular, what we'll do is we'll impose monotonicity of the regression function when we estimate the function. And that will not in general lead to worse convergence rates than we had before without imposing them. But we can also show that in some parts of the parameter space, in particular on and near the boundary of the constraint, we can have much, much faster convergence rates than in the interior of the constraint. This is sort of a special case because the boundary of this constraint, boundary of monotonicity constraints, will involve flat functions, and in principle we're not really interested in estimating flat functions. We rather view this as a result that says in some part of the parameter space you have very, very fast convergence rates. In large parts of the parameter space you have very slow convergence rates. And so in finite samples, in practice, it really, really matters where you are relative to these two extreme cases. And the performance improvements that I'll show you later, they're inherently finite sample. So I don't want to put too much emphasis on convergence rate results here. I really want to argue more that in finite sample we can show or try to explain really why you see much better performance in finite samples when you impose constraints rather when you don't. And so to make this more precise, we also show a non-asymptotic risk bound on the estimator. This is essentially a bound that tells you what the performance of the estimator is for a given sample size n. It's not a convergence rate, it's just the performance for a fixed n. And you can see in this bound later that this bound will depend on how far you are away from the boundary, meaning how far away are you from flat functions. And then I want to show you some simulations which show quite dramatic, I think, improvements in performance when you impose the monotonicity of the regression function relative to when you don't impose this restriction. And so overall, we would hope that this is a positive message to a bit more applied people, perhaps, that these estimators, the non-parametric versions of IV, are perhaps much, much more useful than you might think, given the existing relatively negative literature on this. And they might, in fact, perhaps perform better when you impose these kinds of shape restrictions, assuming they're reasonable in a given context. So I'll want to start with a little bit of background and spend a couple of minutes on ill-posedness and try to roughly explain what is the problem and why are these estimators in general performing so poorly without other constraints. I think it's going to be important to spend a bit of time on number one here to really understand what our results are saying. And so I'll spend a bit of time on this number one part, and the actual results of the paper are in part 2 and 3. And then I show you, hopefully, some graphs. Depending on how much time I have, I might also show you some estimates of demand functions where we impose monotonicity. So let's start with the model. So the model is the standard non-parametric IV model that probably some of you have seen in the literature before. We're interested in this relationship between an outcome y and how it relates to an endogenous variable x, possibly nonlinearly through this function g. And then we have an instrument w, so that the estimation error the regression error epsilon is mean independent of this instrument, given this instrument. All these variables are continuous. So think, for example, of estimating a demand function. You would regress log quantity on log prices. If you worry about prices being endogenous, you might also have instruments W, such as supply shifters, costs that just shift the price around, but are not related to X. Not related to the error epsilon. So it's important to think of these variables as being continuous. In the discrete case, very different sort of problems, or lack thereof. So one way you could estimate this relationship would just be to assume linearity. So this function g is a linear function of x. You still have an instrument w available, and you could just run an IV regression or 2 Sechli squares. And the textbook results would tell you that these coefficients in the linear function can be estimated at a square root n rate. So the error goes to 0 at this rate n to the minus 1/2, which is really, really fast, and ensures nice properties of parametric estimators. Alternatively, you could, if you really worry about nonlinearities in this function g, be a bit more non-parametric on g. For example, it's just an example, think of expanding this function g in polynomials, and if you now impose exogeneity of x rather than endogeneity, so you get the mean independence of x, you can just simply run a non-parametric regression of y on quantities on constant, price, price squared, price cubed, and so forth. If you do that, you get an estimator of the function that's non-parametric as long as you let this number of terms grow with the sample size, and you get this convergence rate. That's also textbook rate that is depends on s, which is the smoothness level of the function you're estimating. So if you have, for example, 2 derivatives of this function g, you put a 2 here, you get 2 over 5, which is a little bit slower than 1 over 2, the parametric case, but maybe not that much slower. So being non-parametric already leads to a little bit of worse performance. It turns out, though, if you put these two things together, endogeneity and nonlinearity in G, and also the first stage actually, the problem becomes, statistically speaking, much, much harder. And so if you put, again, a nonlinear form on G, and you regress now, because of the endogeneity, not just Y on powers of prices, but you use a 2 Sechli squares procedure and some instruments that are now the previous instrument, that is, say, a cost shifter squared, cost shifter cubed, and so forth. This estimator is going to have potentially much, much worse performance than these other two versions above. And I want to spend a couple of minutes explaining why that is. So this is exactly the non-parametric IV problem. This is the one that I'm talking about the rest of the talk. I want to explain why this is such a hard statistical problem and how we get around some of the difficulties with shape restrictions. So to see what's the difference between the linear world and the nonlinear world with endogeneity, I thought maybe it's helpful to think briefly about the linear case and how do we actually get the coefficients beta of interest. If you just look at the normal equations in linear regression, that's what they are. You take expectations up there. And you can simply solve for beta here by making sure that you can divide by this expectation on the right. So you assume it's non-singular. You can put it on the other side. And you have beta being a continuous function of these two expectations. And each of them can be estimated at a very fast rate. And therefore, beta can be estimated at a fast rate as it's a continuous function of these two. In the nonlinear world, the problems are much harder because you cannot do something like this and put these expectations on the other side and assume the eigenvalues being non-zero. So in the nonlinear world, the corresponding equation to the normal equations looks like this. You just take conditional expectations up there. And now we need to solve not for beta, not a vector, but the whole function g, which is inside a conditional expectation, right? And that is a much harder problem for the following reason. So if you write this in terms of functions, on the left-hand side you have a conditional expectation, which is a function of w, the conditioning argument. Call that m. On the right-hand side we have this object of interest, the g function, and it's inside the expectation. So let's call this t operator the conditional expectation operator that's applied to g. Now we need to solve for g, which means we need to invert t, which now is a conditional expectation operator. And that's harder than what we did on the previous slide. The reason is that you cannot simply assume that the singular values of this operator are bounded away from 0. Under weak conditions, these singular values will tend to 0. Therefore, they're not bounded away from 0, and this inversion is difficult to do. So small changes in m might translate actually to large changes of g. And in this sense, g, the object of interest, is not a continuous function of the data. So even if you can estimate m well, these conditional expectations, doesn't necessarily mean you can estimate g well. And that causes all the problems. And this is the source of the ill-posedness in this problem. Right. So the discontinuity of this t, one way to see that is that whenever you take two values, g1 and g2, that are small to one another, continuity of t means that also t applied to these two values, the difference is small. T inverse not being continuous means now the opposite. Whenever these function values on the left are close to one another, it doesn't necessarily mean that g1 and g2 are close to one another. And so one way to measure how bad really is this ill-posedness is by looking at the ratio of these two objects. If they're very similar, so left-hand side small means right-hand side is small, then this ratio is small. So they're close to one another and it's not blowing up this quantity. However, if the left-hand side is small but the right-hand side may not be, it means that the ratio of the two can be very, very large. And so how large this quantity tau is, the ratio of the two, may give you an indication of how bad this ill-posedness is and how severe this discontinuity really is. So this object tau is going to be of central interest in the rest of the large part of the paper, because this tau shows up in the convergence rate of the nonparametric RV estimator. So tau could potentially be very large. It grows with the dimension of the sieve space. So the sieve space here comes in by looking over all these differences h that are linear combinations of polynomials, for example, as we had in the previous slide. So hk, the sieve space, is now just the linear combination of polynomials of order k. And as you let k grow, this tau might go off to infinity. The problem now is that this tau shows up in convergence rates of nonparametric RV estimators. So this two-stage least squares estimator I mentioned before typically has a convergence rate of this form. So there's this variance piece. This is, for those of you who have seen the nonparametric convergence rates before, this is coming from the variance. It's square root of k over n, the number of series terms you use, divided by the sample size. And this variance piece gets blown up by tau, which is going off to infinity, but this goes to 0. So that variance piece is blown up by a bit and therefore goes to 0 quite a bit slower than it would be if the tau wasn't there. And then there's this bias piece, k to the power minus s, and s comes again from the smoothness of the function g. That's also going to 0 at standard rates. It's this piece of the variance that gets blown up by the ill-posedness. And the fact that tau goes to infinity means that the performance of the estimator slows down a lot relative to standard non-parametric estimators. So if you look at what this means in terms of sample size, depends on how this tau goes off to infinity. And in fact, in sense of how discontinuous is this T inverse. You can relate this back to the eigenvalues of this T inverse. So in the case, these are the typical two cases that the literature is looking at. The first one is where the tau goes off to infinity at a polynomial rate. You end up getting a polynomial rate in n for the convergence. And if tau goes off at an exponential rate, that happens, for example, when x and w are jointly normal, then the rate can be really, really terrible. It could be log of n, which is much, much, much slower than square root n or any other polynomial, right? This is a really terrible and very slow convergence rate. So this is the piece that I imagine that might deter quite a lot of people from using non-parametric IV methods, because the performance might be really terrible in this jointly normal situation. Now, suppose we want to estimate this function. That is the true g function. Maybe it doesn't really look like a demand function at the moment, but let's take this as an illustration. This is something that I'll show you more graphs about this in the simulation. So the setup I'll describe a bit more detail later. If you use the non-parametric IV estimator to estimate this function, you may get something like this, say. The blue line is the estimator. It's actually very close to the truth on average. This is averaging over simulation paths, over estimates. And then these dashed lines are indicating pointwise confidence, empirical confidence intervals. So these are 2 standard deviations away from the estimates. And sometimes, though, it turns out you can improve the performance of this estimator quite a bit by putting more restrictions on the problem. So if you knew, for example, that this true function has to be increasing, and you'd only put that extra information into the estimator, you put this constraint that the function has to be increasing into the estimator in some way, you would end up getting this red line. So this is the new estimator, the constraint estimator that's using the fact that the function has to be increasing. And the confidence bands now, these red dashed lines, are actually much, much narrower than the original ones where you didn't impose this constraint. And so that's what most of the paper is going to be about, really trying to explain, offering some explanation for why this estimator that's constrained may actually perform much, much better than the original one here, at least in terms of variance, right? It seems to have much smaller confidence bands. And in fact, the difference can even be much, much more dramatic. I'll show you this in the simulations later. So monotonicity can have quite an effect on the estimator. And we'll try to explain this fact that we see in the finite sample through imposing these 2 constraints, not just monotonicity of G, but also monotonicity of the instrument. We will then first show that a new definition of the tau, this ratio that measures how discontinuous this inverse of t was, as a restricted version of this tau turns out to be bounded in our setup under these 2 restrictions. So the measure of ill-posedness we proposed, and that will show up in our rates, turns out to be bounded and does not go off to infinity as the other one that I showed you before. So just saying that, you would perhaps immediately think that there should be some impact of this finding on the performance of the estimator. And that's what the rest of the paper is going to be about, trying to make a bit more formal what is the effect of this bounded tau on the performance of the estimator. So one way, yeah.
So why are you focusing specifically on monotonicity rather than, say, restrictions that come from economic theory? So you might have some kind of Slutsky.
Yeah, I agree. So in the demand case, you would have Slutsky restrictions, and I agree that would be maybe also an interesting thing to look at. We simply start with monotonicity as a starting point. Our conjecture is that similar results might hold for other constraints. We just simply started with monotonicity because sometimes that economic theory might also give you that directly.
But it might be nicer to motivate it. Say I've got this model and to fit this non-parametric function because I don't know preferences, but there are other restrictions.
Right.
So tell us something about this structure.
At the moment, I was really just thinking of you thinking the demand functions say they should be monotone in your particular application. If you estimate the production function or something else, most economic theory would tell you should be increasing. Sorry?
You might have 2 or 3 prices on the right-hand side.
Yeah, I agree. So it's a bit simplistic in that sense, but we want to make this point that shape restrictions can help a lot potentially, and that is simply a starting point. Yeah, there's a lot more I think that could be done.
Doesn't have any specific role here.
Sorry, what does?
Monotonicity doesn't have a specific role. It's just an example of some kind of shape restriction.
Our results hold for monotonicity, so we don't at the moment have results for other shape restrictions. I would hope you can extend all of this to other restrictions. So yeah, for the moment you should think only of monotonicity. So here's one way you can perhaps look at the impact of the monotonicity constraint on the performance of the estimator. Think of this as an additional constraint on G that you impose. So monotonicity means the derivative should be, so an increasing function means the derivative has to be non-negative. So if you impose this restriction, what is the impact of imposing this restriction? Let's focus first on the interior of this constraint, interior being defined as the cases where this inequality is satisfied strictly. It's very easy to see actually that in terms of convergence rates at least, you cannot get any improvements at all by imposing this restriction. It's very easy to see because any constraint or unconstrained estimator, whether you impose this restriction or you don't, is eventually after some sample size large enough going to be equivalent to the constraint estimator as long as it's estimating the derivative consistently. So any estimator will have the feature that after some n it will be increasing. And so any constrained or unconstrained estimator that has this feature will be equal. They will be equal to each other with probability approaching 1. There cannot be any convergence rate improvements in that case. On the boundary, however, in this case, the derivative being 0 means the function has to be flat. Convergence rate improvements could be possible. And we will show, in fact, that there are some. But we'll go a bit further. We'll actually also show that not only on the boundary do you have convergence rate improvements, you'll also get improvements near the boundary. So in a shrinking neighborhood of the boundary, you will still get convergence rate improvements. Since flat functions are not really the main focus in most economic analysis, we don't really want to sell this as the main point of the paper. It's really not. It's just to show you that the convergence rates might be very, very different in part of the parameter space. And for finite sample, it really, really matters where you are relative to these two extreme cases. And that's really what the paper focuses on, is this last part, to try to explain what happens in the finite sample. So let's maybe get to the results. Before that, I want to just briefly mention a few related papers. As far as we know, people haven't really studied what's the impact of shape restrictions on ill-posedness properties of our problem. But there are some papers, like for example Joel's work with Joachim, in which they use shape restrictions for identification purposes in non-parametric IV. There are also some papers, also by Joel and Richard and Matthias, in which they have noted before that imposing shape restrictions, for example Stochastic restrictions in one of their papers, seemed, at least in simulations, to improve performance of the estimator dramatically. So people have noticed this before. We're not the first ones to do that. But as far as we know, there are not any explanations out there as to why that actually happens. And then there's obviously a large literature on NPIV itself, the optimality of these estimators without shape restrictions, and so forth. So in the statistics literature, people also have looked at shape restrictions quite a lot in standard regressions, but there's no discussion of ill-posedness and how shape restrictions relate to or change maybe ill-posedness properties. Okay, so let's maybe get to the first main result. The first main result is about the tau that I showed you before. I was telling you that the reason why this estimator performs so poorly is that this tau that shows up in the convergence rate goes off to infinity potentially very quickly and therefore slows down the rate. We propose another tau that's slightly restricted and we think makes more sense in our setup where we have additional restrictions. So we define this new tau, a new measure of ill-posedness, that incorporates restrictions on derivatives. So instead of just looking at this ratio over all possible h functions that are linear combinations of some basis, say polynomials, we look only over those h functions that actually incorporate restrictions on the derivative. So think of this A there. If you put a 0, it means that this H space only contains functions whose derivatives are non-negative, which means these are monotone functions, increasing functions in particular. If A gets larger and larger and larger, for example, infinity, these restrictions, there will be no restrictions, and this H space is really the whole space of all possible combinations of polynomials. So making A larger and larger makes this space larger and larger, and that will increase this ratio. On the other hand, making A smaller and smaller would decrease this tau, and the big question is, how much smaller can you make this tau relative to the original tau without the constraint, so that maybe the performance of the estimator is not as much deteriorated by this tau going off to infinity, because the new one is smaller. In fact, we will be able to show that this tau will be bounded. We do this under two assumptions. The first one is the monotone instrument assumption. It looks like this. So we need to have an instrument W that relates to X in some monotone fashion. Monotonicity here means something like stochastic dominance. So the conditional distribution of X given W has to be shifted to the right when you increase the conditioning value, the value of the instrument. In fact, we need this shift to be strict, at least for two values of the instrument. We have continuous instrument at the moment, so there have to be at least two values in the support for which this is actually strict. One way to think about this restriction is in terms of first stage. So if you had a first stage function x, which describes how x depends on the instrument W and some unobservables, you really need monotonicity of this function in the instrument. This is different from control function approaches, right, where you have monotonicity in the unobservables. That's not what this is. This is about monotonicity in the instrument. So cost shifter has to monotonically increase, in a stochastic sense, prices. It's not the unobservables, okay? It's very important. In fact, the unobservables could here be of any dimension. We're not restricting that at all. It's not like in the control function case, right? This is very, very different. That's assumption number one. And then we have some regularity conditions. I don't really want to talk about this too much. We need the density of X and W to be square integrable. We need the densities to be bounded from above, some of them from below, at least over some range, and so forth. But for these two, under these two conditions, we can show the first main result. The tau is bounded. The new tau that I showed you does not go off to infinity like the previous one. This is now bounded uniformly in n, and this constant c over there does not depend on sample size whatsoever. Given that the tau earlier showed up in convergence rates, you would think this should have implications for how the estimator performs, right? And we'll show that in the rest of the paper. And for now, I really just want you to notice that this bound is there completely irrespectively of whether the original problem was severely ill-posed or mildly ill-posed, or in fact how the original tau was going off to infinity. This one will always be bounded, the restricted one, at least for some values A that are not too far away from 0, so not too far away from monotone functions. Particularly when you put 0 there, you get this restricted measure to be bounded for all monotone functions. But there are some non-monotone ones as well, for which it's bounded. Right, so that's the central result, and everything else follows from this. So let's look maybe what are the implications and see how does this bounded tau result come into play for the performance of the estimator. Suppose now we want to actually estimate something. So far everything was in the population, right? So let's now suppose we have a data set on y, x, and w. N is the sample size. We'll pick bases for the two in terms of x and w. Remember that we were originally using two-stage least squares estimators that regress quantities on price, price squared, price cubed, and so forth. That's the first basis p, the polynomial in price. Then you have to pick for the instruments another basis, because you use instruments not only cost shifter, but cost shifter squared, cost shifter cubed, and so forth. That's the second basis q. And then this quantity psi is a very typical object in non-parametrics. It's going to show up in the rate later. This is the maximum that this basis vector can attain. You'll see this in a moment. So psi will be there. Oftentimes that's of the order of square root k, the number of series terms. And now we want to look at the behavior of this estimator g hat, which is two stage least squares as I just described, but imposing the restriction that this resulting estimator of the function g is in fact monotone. So we don't just do two stage least squares to get this beta hat, but when we look for betas that are estimating the true beta, we will at that point impose monotonicity as a linear constraint to find this restricted beta. Now we also impose monotonicity of g itself. And then under these three assumptions, we can get the following main result. And this is where you see how monotonicity plays a role, I hope. So we get a bound. So sorry, this looks a bit long, but let's talk for a moment what this is saying. So this is a bound on the estimation error of the restricted estimator minus the truth. And the bound has some constant here that is independent of n. Then there's a minimum of two pieces, a first piece and a second one, plus this standard bias component. The bias component is k to the minus s. That was there even in the unrestricted case. Now what's really different to the performance that you'd seen at the beginning of this talk is this middle piece with the minimum. So the bound that we can derive under the monotonicity restrictions is different through this minimum. And what's different is that this has two regimes, this bound. So let's look at the first one before in front of the comma. This part does not depend on tau at all. So ill-posedness doesn't show up in the first part of the bound whatsoever. The second piece has a tau in there, and so you would think this tau going off to infinity, this tau now is the original one without imposing constraints. That goes off to infinity, so oftentimes you'd think this second piece being quite large. The rest in here is k over n, so number of series terms divided by n and then square root. This is, and the second piece is typically of a similar order than this, so just forget about the second part for now. Just think of this as k over n square root. That is the standard variance component from non-parametric estimation. Similarly here, it's k over n square root plus something that is typically of the same order or similar order as the first one. So again, just forget about this piece for now. So what are these two regimes? What's really different between the two is that here shows up the maximum value, this maximum norm. It's just the maximum value of the derivative of g. So the derivative here now is going to determine which of the two regimes the bound is in. So if the first piece is smaller than the second, then the bound is in the first regime. So this is the case whenever the derivative is not too large. So this g prime has to be small enough so that the first piece is smaller than the second. That is the case when this condition is holding. So the maximum value of the derivative of the function is smaller than this tau object times something that depends on the sample size. So for some sample sizes, say some smaller sample sizes, this may actually be a pretty large number, this piece on the right, and it's multiplied by tau, which potentially goes off to infinity very quickly. So you would generally think this might at least be a pretty large number. And for a large range of functions g, whose derivative is not 0, but also not too large, at least relative to this, the bound will be in the first regime, and it will be completely independent of tau, meaning independent of ill-posedness. And therefore, you would think that piece should be a relatively small bound. And the estimator is performing well. This is where the monotonicity bound really, the monotonicity constraint really matters. The fact that tau doesn't show up comes from the fact that tau is bounded for monotone functions and functions that are close to monotone. However, when the sample size n increases, this piece is going to 0. This is still going to infinity, but the overall term is going down. And so eventually, for some really large sample sizes, the derivative of the function, the maximum value of the derivative, may actually be bigger than this. And so the bound turns over into the second regime, which is the second piece, and now ill-posedness comes back into play. So I think one way to summarize this result might be the following. one corollary of this is that for n large enough, the first piece is not going to matter. For n potentially really, really large, you will end up having the second piece dominating, and that is the standard, ends up determining the standard convergence rates, which look like this. It's tau times the variance part plus bias, the standard object that could potentially be slow. That's in general. But then if you have the special situation where this derivative actually tends to 0, so it's a shrinking neighborhood of the boundary where the derivatives of the functions get smaller and smaller and smaller, you can make sure that the first piece is always dominating, and it's always the smaller piece. So you never end up having the tau showing up. And therefore, at least in the neighborhood, this particularly shrinking neighborhood of the boundary of flat functions, you can actually get a convergence rate that is completely independent of tau. And there's no ill-posedness whatsoever. So it's much, much faster convergence rate, and the estimator is expected to perform really, really well. This is in terms of convergence rates, and in finite samples, convergence rates probably don't matter too much. So what really matters much more is, in a given sample n, for size n, how well does the estimator perform? Well, that will really depend on the relative magnitudes of these two minimum pieces from before, and that will mainly depend on how large is this maximum value of the derivative relative to this piece, which potentially might be very large because of the tau. That might be very large. So let me maybe wrap up by just showing you one graph from before. I wanted to argue that imposing restrictions, in fact, give you much better performance of the estimator. And one way to see that in the graph was by looking at the variance that is diminished by quite a lot. But this graph actually can be much more dramatic. And so in the paper, we have MSE ratios, so mean squared errors of constrained versus unconstrained estimators might be ratios that are very close to 0. So what this is saying is that the mean squared error of the restricted estimator that imposes monotonicity is a factor 10 times smaller than the one that is not restricting the function by monotonicity. So I just want to finish with the point that this difference can be huge, much bigger than this graph might actually suggest. So let me stop there. Thank you very much.
Okay, well, this is in some ways a very impressive paper. As you saw from one of the slides that Daniel presented, there's a very large statistics literature on dealing with shape restrictions, mostly monotonicity restrictions, mostly applied to conditional mean non-parametric estimates of conditional mean functions. And one of the messages from this literature is that dealing with this problem is extremely complicated. And the reason why it's extremely complicated is because you basically don't know where the shape constraint is binding and where it's not. And somehow in the estimation process, you have to deal with that. There's another even larger literature going back, I don't know, about 130, 40 years on ill-posed inverse problems. So and these two streams have been more or less separate. So Daniel and Dennis are trying to bring them together and produce finite sample results. So this is a very impressive piece of work in that regard. Okay, so let me give you a little background. So the paper is about non-parametric estimation of this unknown function. And x is a scalar random variable that might be endogenous, and w is an instrument for x, and u is an unobserved random variable, and the expected value of u conditional on x is not necessarily equal to 0. So the model is equivalent to this operator equation in the top line here that Daniel showed you. And the problem is that this operator T, you can think of as being an infinity by infinity matrix. In fact, if you write this thing in a Fourier representation, that's exactly what it is. And the problem with an infinity by infinity matrix as opposed to a finite dimensional matrix is that there are infinitely many eigenvalues that are arbitrarily close to 0. That's the source of the ill-posed inverse problem. Earlier, somebody was asking about the norm, and does the norm matter? Actually, it doesn't matter, because the problem is that this g function in a Fourier representation is the sum of some coefficient that you can easily estimate divided by an eigenvalue times a basis function. And if the eigenvalues are converging to 0 very rapidly, you know, you get something divided by something converging to 0 very rapidly. That's the source of the problem. So the mathematical statement is that T inverse is unbounded. And so the rate of convergence of an estimator to G can be very slow, like logarithmic, as Daniel showed. So this has been known for over 100 years because this TG equals M thing is a Fredholm equation of the first kind, and it's turned out to be extremely important in mathematics and image denoising and medical imaging. And in fact, whether some people can live or not depends on whether this problem is solved correctly. So there's a huge literature on these kinds of problems. All right, so what this paper does is it adds shape restrictions. So, and you can see what they are, and the authors argue, and I agree with them, that these shape restrictions are reasonable in many applications. And then the paper itself provides methods for testing the shape restriction assumptions and some other things which Daniel didn't talk about, and I won't either. Okay, now the question is, does the shape restriction accelerate, or a question is, does the shape restriction accelerate convergence? So in general it doesn't, because in general the shape restriction is not binding and is far from binding. So the next question that's relevant to this paper is, does the rate of convergence increase if the derivative is close to 0 in some sense? So at least for some values of x, and x is in some compact interval, say 0 to 1. So the paper's answer is a qualified yes. And it's qualified because the answer depends on, frankly, an unusual definition of the rate of convergence. And it also depends on what it means by the derivative is close to 0. So the first unusual feature is that the rate of convergence is usually stated in terms of the L2 rate, or the integrated mean squared error, which is this thing here. But the results in this paper are stated in terms of a truncated version of this norm. So instead of integrating, if the support of x is 0 to 1, instead of integrating from 0 to 1, they integrate from x1 to x2, and x1 is strictly greater than 0 and x2 is strictly less than 1. And it turns out that the difference between this norm and that norm is not innocuous. And I'll talk about that a little more later. Okay, now the main result is they let G hat be a sieve estimator. So basically, it's represented as an infinite series. And the problem, the estimation problem is to estimate the Fourier coefficients. And so they do that. And what they show is if the derivative is close to 0 in this sense, so it's within this distance of 0, where S is some smoothness parameter, then, and some other conditions hold that Daniel talked about briefly, and I won't talk about at all, then you get this fast rate of convergence. Well, you get this, it's not just a rate of convergence, you get this exact finite sample inequality in this truncated norm, not in the ordinary L2 norm, but in the truncated norm. The result is non-asymptotic, and the rate of convergence that's implied by this result is much faster than can be achieved without the shape restriction. So that's basically what Daniel was showing. Now the question is, what can we make of this? In the first place, any shape restriction, not just monotonicity, that binds in at least a small part of the support is going to reduce the integrated mean squared error. Why is that going to happen? Because estimation amounts to solving an optimization problem. Now you're solving the same optimization problem but with a constraint. So the feasible region for the constrained optimization problem is smaller than the feasible region for the unconstrained one. So of course, the unconstrained estimator is going to perform worse, or the constrained estimator is going to perform better in a finite sample than the unconstrained estimator does. So we don't need any theory to reach that conclusion. We just need to know that the constrained feasible region is smaller than the unconstrained one. And that by itself could explain the numerical results that are in the paper, especially when the function that's being estimated in these simulations is far from monotonic. Now the next question then is, so given that we know this, do the theoretical results provide further insight? So as the paper points out, the fast convergence rate holds only if the derivative of the function being estimated is in a neighborhood of 0 everywhere. The result, and the paper is quite explicit about this actually, the result does not hold if the function is flat in some places and strictly increasing in others. So in particular, the theoretical result does not apply to the function that, that was in the graph that Daniel showed. Although the improvement performance due to having a smaller feasible region, of course, does apply. So the fast convergence rate really applies only to a very restricted class of functions, namely that are within the shrinking neighborhood of being flat. Secondly, the constant that's in this inequality that they have applies only for the truncated norm. And if the bounds on this truncated norm approach 0 and 1, the constant increases without bound. So we're really talking, now the authors think that this may be an artifact of their method of proof. That's not clear. But at least as it stands, the problem is that this truncated norm is essential, and so it's not innocuous, and you don't get the result in the usual norm. Then the third thing is this really a super efficiency result? So suppose we just want to estimate a scalar parameter theta, and this theta is within n to the minus fourth of 0. Then, this famous result of Hodges from 1951 that was never published because he thought it was too simple, but Lucien Lacan built his whole career on it. An estimator, you can make an estimator theta that converges to 0 more rapidly than the maximum likelihood estimator, which converges to the rate n to the minus a half. So you get this super efficiency result. You also get super efficiency if you have, say, a non-parametric kernel density estimator that's twice continuously differentiable. And if the kernel density estimator is contained if the second derivative is in this neighborhood of 0, so bigger than n to the minus a fifth, then you get almost a root n rate of convergence on the density estimator. So these kinds of super efficiency results have been known for 65 years. And the way that they are dealt with normally is treating super efficiency as a pathology and requiring and defining efficiency to mean that whatever the rate of convergence is holds uniformly over a fixed set of non-zero Lebesgue measure in the case of estimating theta. In the case of density estimation, it's over a smoothness class, not over some small neighborhood. And it's over a fixed class in non-parametric IV estimation. You can see this in the paper by Chen and Rice. So this paper's result, in fact, does not hold when we're talking about a fixed class of functions. It holds only if we're talking about the shrinking neighborhood, which looks, I don't know if it really is, but it certainly looks a lot like super efficiency. So the conclusions are that, or my conclusions are that this paper provides a non-asymptotic bound, and this is it's difficult to achieve non-asymptotic results in this business. So this is a very impressive accomplishment. And it provides methods for testing the monotonicity assumptions, which neither Daniel or I talked about. But the non-asymptotic bound that they have is for a very limited class of functions. It uses a norm that differs from the usual one in a way that is not innocuous. And perhaps what we really are seeing here is a super efficiency result, not something more general and applicable.